Assalamu alaikum class. Today is our 22nd lecture of analytic geometry. In the previous lecture, we have discussed a straight line as an intersection of two planes, two intersecting planes which are obviously non-parallel. Um, now we will discuss some more examples to understand the topic more clearly in this lecture. Show that the straight line x over minus 1 equals to y plus 1 over 2 equals to z minus 2 over minus 5, which is equation of symmetry, equation of symmetry of line, and the equation of plane is given by 3x plus 4y minus 2z equals to 22. Now we have to find out the unique point of intersection, and we also find the point of intersection between the equation 1 and 2. Solution. Any point on the straight line 1 has coordinates, and these coordinates are obtained if we set equation number 1, which is the symmetric equation of line x over minus 1 equal to y plus 1 over 2 equals to z minus 2 over minus 5. We will set this equation with another parameter t. Then it gives x equals to minus t, y equals to minus 1 plus 2t. Similarly, z equals to 2 minus 5t. So equation number 1 has the point with coordinates minus t, minus 1 plus 2t, 2 minus 5t. If this point lies on the plane 2, so it must satisfy the equation 2. So we have 3. Substituting these values in by replacing the values of x, y and z with the values of minus t, minus 1 plus 2t, 2 minus 5t respectively, we will have 3 minus t plus 4 times minus 1 plus 2t minus 2, 2 minus 5t equals to 22. After solving the brackets, we are left with minus 3t minus 4 plus 8t minus 4 plus 10t equals to 22. That gives 15t equals to 30. Taking 5 as a common factor, we are left taking 5 or 15 as a common factor, we are left with t equals to 2. Hence, the point of intersection becomes minus 2, 3, minus 8. Right? This point is obtained when we will substitute in the values of x, y, z, which are given by x equals to minus t. So the point x becomes x equals to minus 2, and y is equals to minus 1 plus 2t. Substituting the value of t, we will get y equals to 3. Similarly, z is equal to 2 minus 5t. After substituting the value of t equals to 2, we are left with z equals to minus 8, which is actually the point of intersection of these two equations. Example number 18, in which we have shown that the straight line L with parametric equation x equals to minus t, y equals to minus 1 plus 2t, and z equals to 2 minus 5t is parallel to the plane minus x plus 2y plus z equals to 3. Solution. A symmetric form of the equations of L is given by ये जो भी हमें 3 साइमल्टेनियस इक्वेशंस पैरामीट्रिक इक्वेशंस दी हुई हैं उनको अरेंज कर देंगे सिमेट्रिक फॉर्म के अंदर, तो इट विल गिव x over minus 1 which is equal to y plus 1 over 2 which is equal to z minus 2 over minus 5, and direction vectors c1, c2, c3 are given by minus 1, 2, minus 5. Here the points x1, y1, z1 which lies on the line are given by 0, -1, 2. As you can see that the general form of the symmetric form of the equation of line is given by x minus x naught over a, which is equal to y minus y naught over b, which is equal to z minus z naught over c. Here, where a, b and c are the coefficient of the planes, which gives the value a equals to -1, b equals to 2 and c equals to 1. Now ax1 plus by1 plus cz1 is given by, after substituting the values of a, b, c and the point x1, y1, z1, we will get a0 x0 times -1, it gives 0, plus b 2 times -1 plus 1 times 2, it gives 2, which gives the answer -2 plus 2, which is equal to 0, but it does not equal to 3, which is required in the equation of plane. That means we have AC1 plus BC2 plus CC3 equals to -1 times -1 plus 2 times 2 plus 1 minus 5, 1 times -5, which gives 0, which shows that the given straight line is parallel to the given plane, and which is the required solution. In example number 19, show that the straight line x equals to z minus 4, y equals to 2z minus 3 lies in the plane 2x minus 3y plus 4z minus 1 equals to 0. Now we have to show that the given line lies in the plane. So its points must satisfy the equation of the plane. Solution is given by, a symmetric form of the equation of the straight line is given by x plus 4 by 1 equals to y plus 3 by 2 equals to z over 1. Here the points with coordinates are x1, y1, z1 is given by -4, -3, 0, where a, b, c, which are the coefficients of the equation of the plane, are given by a equals to 2, b equals to -3 and c equals to 4. The direction vectors c1, c2, c3 from the symmetric form of the equation of the straight line is given by 1, 2, 1. Therefore, ax1 plus by1 plus cz1 minus 1 equals to, substituting the values of a, b, c and the point x1, y1, z1, we will have 2 times -4 minus 3 times -3 plus 4 times 0 minus 1, which gives -8 plus 9 plus 0 minus 1, and the resultant is 0, which shows that it satisfies the equation of plane. And AC1 plus BC2 plus CC3 is given by 2 times, substituting the direction vectors in the given equation of the plane, general equation of the plane, we are left with 2 times 1 minus 3 times 2 plus 4 times 1 equals to 0, which gives 2 minus 6 plus 4, which gives -6 plus 6 equals to 0. Thus, the straight line lies in the plane. In example number 20, we have to find an equation of the plane through the straight line. And the straight line is given by the symmetric equation x minus alpha over L, which is equal to y minus beta over m, equal to z minus gamma over n, and parallel to the straight line x over L dash equals to y over m dash, z over n dash. Now the solution is, we are given with the symmetric equation, equation number 1 of the line x minus alpha over L, y minus beta over m, and z minus gamma over n. If we write the parametric equation of equation number 1, then we have x minus alpha L, x minus alpha L equals to y minus beta over m, z minus gamma over n equals to k. We set the equation number 1 with the third parametric value k. Then it gives x equals to a plus lt, y equals to beta plus mt, equals to z equals to gamma plus nt. So a plane which is passing through equation number 1 is given by a x minus alpha plus beta y b times y minus beta plus c times z minus gamma equals to 0. Now substituting the values of x minus alpha which we have taken lt, so substituting alt plus b bmt plus c and d, which is equals to 0, taking t as a common from the equation, and t is a parameter which is a non-zero, so it is not equal to 0. So we have al plus bm plus cn equals to 0 in said equation number 4. Since the plane 3 is parallel to the straight line given in equation number 2, so we have al dash plus bm dash plus cn dash equals to 0. Eliminating the coefficients a, b, c from equation 3, 4 and 5, so the required equation of the plane is given by solving the determinant x minus alpha, y minus beta, z minus gamma, and from equation number 4 we have L, M, N. From equation number 5 we have L dash, M dash, N dash. Solving this determinant, which is equal to 0, we are left with summation x minus alpha times Mn dash minus M dash N, which is equals to 0, which is the required equation of the plane which is passing through the straight line and is parallel to the given straight line. Find the condition that the two straight lines x minus alpha over c1 equals to y minus beta over c2 equals to z minus gamma over c3, state equation number 1, and a x minus alpha dash over d1 equals to y minus beta dash over d2 equals to z minus gamma dash over d3, state equation number 2 may be coplanar. Also we have to find an equation of the plane containing them. So first of all, the equation of the plane containing the first line is given by a times x minus alpha plus b times y minus beta plus c times z minus gamma equals to 0, say it equation number 3. From equation number 1, which is equation of a symmetric equation of the line, take x minus alpha over c1 equals to y minus beta over c2 equals to z minus gamma over c3 equals to t, where t is a parameter. So the value of x minus alpha becomes c1t. Similarly, y minus beta equals to c2t, z minus gamma equals to c3t. Putting these values in equation number 3, we got AC1T plus BC2T plus CC3T equals to 0, taking T as common. Since T is a perimeter, so it cannot be 0. Therefore, AC1 plus BC2 plus CC3 equals to 0, which is an equation number 4. If this plane contains the straight line 2, then the equation becomes A alpha minus alpha dash plus B beta minus beta dash plus C gamma minus gamma dash equals to 0. Set equation number 5, where AD1 plus BD2 plus CD3 equals to 0 in set equation number 6. Now eliminating the coefficients A, B and C from the equations 4, 5 and 6, the required condition is in the form of determinant alpha minus alpha dash, beta minus beta dash, gamma minus gamma dash, C1, C2, C3, D1, D2, D3. The determinant is equals to 0, which gives summation alpha minus alpha dash times C2 D3 minus C3 D2 equals to 0. If this condition is satisfied, then an equation of the plane containing the two straight lines is obtained by eliminating A, B, C from 3, 4 and 6, and it is given by x minus alpha dash, y minus beta dash, z minus gamma dash, C1, C2, C3, D1, D2, D3 determinant equals to 0, which gives summation x minus alpha dash times C2 D3 minus C3 D2 equals to 0. Glossary, it's for reinforcement. Direction vector, a vector parallel to a line that is used to describe the direction or orientation of the line in space. Journal form of a equation of a plane is given by ax plus by plus cz plus d equals to 0, where n vector has coordinates abc, is a normal vector of the plane with points x0, y0, z0, which lies on the plane, and d equals to ax0 minus by0 minus cz0. ये वो सब इक्वेशंस और सब डेफिनेशंस हैं जो अभी आप पिछले लेक्चर्स में पढ़ चुके हैं. Normal vector, a vector perpendicular to a plane. Parametric equation of a line, the set of equations x equals to x naught plus dA, y equals to y naught plus dB, and z equals to z naught plus dC, describing the line with direction vectors v equals to abc passing through the point x naught, y naught, z naught. If we want to write the symmetric equation for the line, then we will have x minus x naught over a equals to y minus y naught over b equals to z minus z naught over c, which is obviously equal to the parameter t. Scalar equation of a plane. The equation a times x minus x naught plus b times y minus y naught plus c z minus z naught equals to 0, used to describe a plane containing point P, which is equals to x naught, y naught, z naught with normal vectors a, b, c, or its alternate form ax plus by plus cz plus d equals to 0, where d equals to ax naught minus by naught minus cz naught. Similarly, we have another definition, skew lines. The two lines that are not parallel but do not intersect, that lines are called skew lines. मीन्स वो पैरेलल तो हों लेकिन इंटरसेक्ट ना करें, पैरेलल ना हो और इंटरसेक्ट भी ना करें. Symmetric equation of a line. The equations x minus x naught over a, y minus y naught over b equals to z minus z naught over c, describing the line with direction vectors v equals to a, b, c passing through the point x naught, y naught, z naught. Vector equation of a line. The equation r equals to r naught plus t we use to describe a line with direction vector v having direction vectors a, b, c passing through the point P x naught, y naught, z naught, where r naught, x naught, y naught, z naught is the position vector of point P. Vector equation of a plane. The equation n dot pq equals to 0, where p is given point in the plane, q is any point in the plane, and n is normal vector of the plane.